Hi, my name is Ali Shesava from Breach Digital, and welcome to this point of load and power supply design webinar with TI and Breacher. We are going to talk about how you would design using WEBENCH over the next hour or so. So the aim of the webinar is to speed up your power supply point of load and power supply design for your product by using WEBENCH Power Designer. Also, we'd like to be able to help you quickly decide what technology, which IC, which control method is best for your application. What we're going to do over the next hour is we're going to talk about how you select the correct IC, what's the difference between a module versus a converter, which one is a controller and which one is the best one for you, how you find a good compromise between the cost and the size and the switching frequency and efficiency, again, as per your application. And we talk about different control methods such as constant on times, voltage mode, current mode, and how you select the right one that is good for your product. Then we're going to do a step-by-step design using WEBENCH. So we have lots of really nice demos to show you how you actually use this tool. And then we delve into advanced features of WEBENCH, whereby we talk about stability and loop design, EMI filter design, and we also look at transformer design for a flyback. So WEBENCH Power Designer, what is it? What does it do? It's a very powerful free online power supply design tool. It selects the right switching regulator, DC-DC or AC-DC, and designs the application circuit with the bill of materials, and it calculates the operating values for you as well. It allows very quick electrical simulation to analyze the performance, and you can get everything exported as a PDF report or even PCB CAD files that you can do very quick prototyping. It supports a whole host of topologies. Most of the common ones are covered: buck boost, SEPIC. It even does PFCs and phase shift full bridge and LLC, and hopefully one of these will fit the criteria for your product. How does the design flow work? Well, step one, you tell the tool, to WEBENCH, what your input and output voltages and currents is going to be. Step two, you have to tell WEBENCH whether it's your priority for you is low cost, a small footprint, high efficiency, or a nice compromise in the middle. WEBENCH needs this information in order to hone in on exactly the design that is suitable for you. We'll do one very shortly. Then you just click on View Designs, and you'll find that when you do that, you get a lot of designs, sometimes over 200 designs. So then WEBENCH gives you many filters whereby you can filter down and narrow down your choices from 200 designs into a handful of designs. And we're going to talk about that shortly and how you intelligently and quickly can get WEBENCH to just hone in on what is best for your application. And after you have narrowed down your choices, you select one or you select two, you do the simulation, you have a look at the design, and then many times there's also an EVM that you can buy in order to carry on your testing. Finally, when you're done, you can create your report, you can get the CAD files, and that's it. So when you open up WEBENCH, it looks something like this. You've got your input, you've got your output. So step one is that you type in your input specification, which is usually just a minimum voltage and maximum voltage at your input. And then you type in your output voltage and current specification. In this particular case, is 3.3 volts and 2 amps. And then step two, you tell WEBENCH what is your priority, whether it's a low cost, high efficiency, or small footprint, or balanced. And balanced will give you a nice compromise in the middle. We are going to talk about this in a minute, the relationship between the size and efficiency and so on. Finally, you click on View Designs, and WEBENCH suddenly will create you, as you can see, a whole bunch of designs. With just that specification alone, you have over 200 solutions. Now, we will need to narrow this down, and therefore WEBENCH also allows you to filter things down. So you got a set of very powerful filters, and as you give more information to WEBENCH to tell the tool what is your requirements, these 280 designs get lower and lower and lower until you just come to a handful. The filters are here on the left hand side of the screen. So Finally, you compare and customize until you're happy with it, then you simulate it, and then you export the CAD file. Okay, and here you can see that it allows you to customize, simulate, and export. So before we can do our first hands-on lab, we need to talk a little bit about the relationship between the switching frequency versus efficiency versus size. Now, assuming that the same specification is being applied to the power supply, then normally in order to reduce the size, we have to increase the switching frequency. The higher the switching frequency, the smaller the size. But if you increase the switching frequency, your switching losses will go up and therefore the efficiency will come down. So you can see that there is a relationship here. Now, in order to increase the efficiency, you can reduce the switching frequency. But of course, if you reduce the switching frequency, in particular, your passive components become big and expensive and the footprint of the power supply becomes big. And as you can see, there's a compromise to be made here. And that is why WEBENCH asks you this question right at the beginning. What is important for your application? Is it size? Is it cost? Is it efficiency? Now, here I have made a design whereby I have told WEBENCH that footprint is the most important thing. And what it has done is that it has selected a very small passive components. And in order to do that, it has automatically increased the switching frequency. Here, I have redesigned exactly the same power supply with the same specifications, but this time I have told WEBENCH that I want a nice compromise in the middle. So we've got lower switching frequency, medium switching frequency, and you can see that the inductor and the capacitor have become bigger compared to the high switching frequency one, which was lower efficiency. Finally, I have told WEBENCH that I want really efficient power supply and size is not too important. So WEBENCH has brought down the switching frequency. The passive components have become very big, but the power supply is more efficient. And you see, that is how you, right at the onset, you can tell WEBENCH which direction your power supply is going. So if we select balanced in step 2, we typically get something in the middle, which is this one here. Okay, then finally what we'll do, we say view designs, and then we go to step 4. After you press view design, as I said earlier on, you get many, many designs, and then you use filters to narrow them down. So what are these filters? So one would be whether you want a module, or whether you want a converter, or whether you want a controller as your integrated circuit. We'll talk about this a little in a moment and tell you a difference. The other one is you may decide that the efficiency has to be above 90%. So you take this slider here and you move it up. And as you do that, the number of designs will be reduced. So there are also filters for control modes, such as voltage mode, current mode, and whether you want synchronous rectification or not, and a whole bunch of other features. Is it automotive? Is it not automotive? And as you select these, you narrow down the choices. So we will soon design several power supplies, but in order to use the full power of WEBENCH, we need to talk a little bit about what these filters actually mean first so that we can intelligently select them. First, regulator type. What is the best regulator type or most suitable regulator type for your application? First, we have switching modules. Switching module is a complete solution in one package. It's an IC or a die completely in one package and includes the controller, the control loop, the switches, the inductor, everything in one. So this is by far the quickest and easiest way and with the smallest footprint way of getting your product into the market because everything is optimized. It's more expensive and more limited, obviously, because the switch and the inductor are now internal and fixed. Then we've got switching regulator. Now that is a complete solution again, like the module, but this time the inductor is outside. So the control loop and the controller and the switches are inside of the integrated circuit, but the inductor is outside. You still have relatively a small footprint because for the whole thing, but the inductor is going to have to sit outside. So as a result, it will be bigger usually than the switching module. It's usually cheaper, but it's more flexible because you've at least got a choice on the size of the inductor, whilst with a module, you couldn't really change the inductor because it was internal. Then we have got switching controllers. Now, switching controller is the traditional PWM IC. It's the most flexible choice of all because both the switch and the inductor is outside and the control loop components are also outside. So you pretty much have to do everything. That makes it extremely flexible and versatile, also very cheap. But obviously you have to buy the inductor, you have to buy the switch. You need a longer development time because you need to do the control loop design. But of course, WEBENCH will design the control loop for you. You need to do the PCB routing and so on. And that is where we use the power of WEBENCH in order to help you get your product designed very quickly. Then, which control mode best for you? We have decided on the different IC packages and what's inside them. Now, which control mode? Now, there are three major categories. There are many others, but there are three major ones which are very popular. One of them is the hysteretic modes, and that is modes such as constant on time, decap, decap 2, decap 3. These are very quick and fast in terms of getting your power supply working. They are cheap, they're easy, they have fast response, they've got good efficiency, and they don't have any stability problems. So you can imagine that you don't have to worry about the stability. That will really speed up your design. However, they have more ripple than other control methods, and the frequency is not fixed. And of course, if the frequency is not fixed, then it will have an unpredictable EMI spectrum, which makes the designing of the EMI filter a little bit harder. Next category is voltage mode. That is, again, cheap and simple. This is now fixed frequency. It's used all the time for buck converters. It's very often used for buck converters. In continuous conduction mode, it's not suitable for boost, buck boost, flyback, SEPIC, or anything that has got a right-hand plane 0. For that, you need current mode. The issue with voltage mode is that it's got poor or slow transient performance under discontinuous conduction mode. So what happens is, at least if you're not using synchronous rectification, we're going to talk about that shortly, if the current falls below a certain threshold on the low loads, then the transient response becomes very slow with voltage mode. The other issue with voltage mode is that if the input voltage starts to vary, it will take a longer time for voltage mode's control loop to react to that. So line regulation is not as great as it can be in current mode. So in order to solve these problems, what we have is peak current mode control. It comes in two flavors, a standard or emulated current mode. It's got faster transient response than voltage mode during input voltage variations. It has got good performance in both discontinuous conduction mode and continuous conduction mode. It's ideal for converters with right-hand plane 0, such as boost, buck boost, flybacks, and so on. The performance when the duty is very, very small tends to deteriorate, and that is because you're trying to detect the peak of the inductor current, and of course when the duty is very small, it's hard to detect that. And for small duties, then you use emulated current mode, whereby it uses a mathematical model in order to predict where the peak is. Then, which type of rectification is best for you? You've heard, I'm sure, that people talk about synchronous rectification and non-synchronous rectification. Now, normal means non-synchronous, and then, of course, we've got synchronous. Note that non-synchronous or normal is not explicitly specified in WEBENCH. So unless it says it's synchronous, then WEBENCH means it's non-synchronous, it's normal. Yeah. Now, where would you use synchronous versus non-synchronous? So, non-synchronous is when you've got an upper side switch and a lower side diode. It's cheaper, less efficient on the continuous conduction mode than the equivalent synchronous version, but it's more efficient until discontinuous conduction mode. So it depends on whether your power supply is going to be operating predominantly in continuous conduction mode or discontinuous conduction mode. So for most of the buck converters, we are almost always in continuous conduction mode, unless our load becomes very low. The transient performance on the low loads is for non-synchronous is poor if you're in voltage mode. In current mode is not as bad. Now, if you need high load efficiency and good transient performance on the low loads, then when you're in discontinuous conduction mode, then you need to tell WEBENCH to use synchronous rectification, right? Or go and do current mode. Yeah. Again, for low load efficiencies, you still have to do in current mode, you still have to do synchronous rectification. So synchronous rectification usually is more expensive. You've got 2 switches instead of 1 switch and a diode, but it's got better performance on the discontinuous conduction mode compared to non-synchronous. It's more efficient in higher loads, i.e. when you're in continuous conduction mode, but less efficient on the discontinuous conduction mode. And in order to overcome this disadvantage of being less efficient in discontinuous conduction mode, so if you need efficiency on the discontinuous conduction mode, then you have to select an extra filter in WEBENCH and say that you want synchronous rectification with diode emulation. And that is a nice compromise between synchronous and non-synchronous, whereby with synchronous rectification plus diode emulation, you will get good efficiency at low loads, also good efficiency at high loads. So we have covered the filtering criteria, at least some of it. So let us now do a hands-on design and see how we use these filters in order to quickly get to a design. The design objective for this lab is to get familiar with WEBENCH, learn to use the filters, select the correct control mode and the IC type, just like we discussed, and create an engineering report and perhaps look at the CAD files that it allows us to export. The designer specification is 14 to 22 volts DC and 3.3 volts for the input and 3.3 volts and 2 amps for the output. This is actually the default specification for WEBENCH. So when you open that, this is exactly what you'll see. Then let us assume that it's a project which is late and therefore you have very little development time, so you have to get it out of the door extremely quickly and you don't want to waste time with the stability problems. You also want to get through the EMC quickly. Now the output ripple is not too important for us. Again, this is part of our specification, and you've got a small footprint is your top priority. So in summary, you don't have space, you don't have time, you can tolerate ripple, and that's important. You don't want stability headaches, and cost is not too critical, which was this final point here. So a module with constant uptime from the discussions that we have had seems to be a good choice. So let us now try and design one with WEBENCH and see what we get. Okay, so here I have got WEBENCH opened on TI's website. All you have to do to get here is to Google TI WEBENCH and you immediately get to this point. The specification is the default, so we don't have to type anything in. You have got 14 volts minimum input voltage, 22 volts maximum input voltage, output of 3.3 volts and 2 amps. And we got to go for balanced design for now, and then I'm going to do view design. So just click on view designs. WEBENCH takes a few seconds, and there we go. You have got 280 matches, which is our choices. Now, as I said earlier on, we are going to try and narrow these down. So first of all, we've got 280 matches. We know that from the specification that time is very, very short, money is not that important, and space is very, very short. So a power module whereby the inductor and the switch is internal seems to be a very good option. So as soon as I click on this, have a look at these 280 and see what happens to it. I click on the filter and 280 immediately goes down to 21 matches. Okay. Now, we also said that what we would like is stability was not important. I rephrase. Ripple was not important. We didn't want headaches for the stability. So if ripple is not too important, then we can go for one of the hysteretic packages. So if you go down to the control mode, you've got constant on-time, DPAC, and so on. These are variable frequency. Let's go for constant on-time, and suddenly 21 matches goes down to 4. Right? So let us take the first design. I can take and customize the design. I can simulate it, and then I can export it. First, let us simulate it because it will take a few minutes, and then we go and look at the other features. So I'm starting a simulation now. So I'm going to do a load transient, and I'm going to say start. Now, at this point, it will start simulating. It will take a few minutes. So whilst it is simulating, let's go and look at the other things that we can do. So I can go to customize. Here is the circuit. You can see that there are very few components because almost everything is internal. There is no inductor, there is no switches. and you only have a few a potential divider with a little bit of output capacitance, and the design is complete. You can download this, and you can see the operating conditions here that WEBENCH has created for you: total BOM, the footprint area, power output, switching frequency, and so on. So I can press download, and here you can see that you can download various files in different CAD packages for Eagle, for OrCAD, and so on. I can change the optimization. I can turn around and say design it in a different way, but that will be restarting. So because we're going to give you so many different examples, I'm not going to do that. But you can look at the PCB layout. So if I look at the PCB layout, you can see that it's laid it out for you. At least it's recommending for you how to be laying this out. And then here you've got the choice of the IC, the capacitors, the MOSFETs, and so on. And here you've got the complete bill of materials. So let us go back to simulate. Actually, no, let us first go to export and see what we can export. If you come to export, again, you've got the schematic, you've got the PCB layout, you've got the bill of materials, and if you say print report, it will create, it's printing the report, it'll create a PDF file, which you can open, and of course, you've got a very nice report, including all the plots and curves and graphs and so on, with the bill of materials and the circuit diagram. Now, let's go back and let's go to our simulate, and you'll see that our simulation is now complete. When this tick box is green, we know that simulation is complete. I can click on it, and there we go. We've got a very nice load transient. The red line here is the step that we have given to the power supply, and the gray line is actually our output voltage. And you can see, if I zoom in, that is recovering very nicely. This is just your switching ripple. You can see that it's recovering very fast, and there is no apart from this one peak, there is no ringing or anything, so it's nice and stable. You can select markers and you can start moving around and seeing what's going on. So there we go. This was our first design. We covered how you very quickly design a power supply. All you have to do is export. You can actually order the bits and pieces directly just pressing the order. You can download the datasheet. You can share your design. And the design is done. You can buy the EVM and you can do some testings and in real life. Let us now go back to the slides and we talk about a stability and fixed frequency switching. Okay, so on the previous example, we used a module in order to get a product very quickly. Also, we used constant on-time, whereby the frequency was variable. We could do this because the specification said that we didn't need too much, we were not too bothered about the ripple. Now, many times you can't do that, and for that you have to go into fixed frequency switching, voltage mode, current mode, and so on. And then there may be a stability issue, and that is why WEBENCH also designs the control loop and make sure that these are stable. So first thing that we need to do is we need to understand what to look for on a Bode plot, and what information is it that that WEBENCH is trying to give to us. Yeah. So WEBENCH specifies three important parameters for us to assess the stability. One of them is crossover frequency, another one is the phase margin, and the other one is the gain margin. So in the next slide, we're going to talk about these things, and this is what we're going to look at on the WEBENCH report to make sure that they meet the stability criteria. So all you need to know when WEBENCH creates your design is what to look for. Now, this is a Bode plot, that is the gain plot, this is the phase plot. Many times these two are superimposed on top of each other and you've got two axes. Maybe you've got gain on this side and you've got phase on this side. But we said that we've got crossover frequency, phase margin, and gain margin. So first, the crossover frequency. Crossover frequency is the frequency at which the gain plot, this is this blue line here, crosses the 0 dB axis. And that is a measure of how fast our power supply recovers from from a step. There we go. So if you take that 0 dB line, you draw a line up to here until you hit the curve, and then you go down and you look at the frequency on the x-axis, you'll see that the crossover frequency in this case is 28 kilohertz. Now, we recommend that your crossover frequency is around 1/10 of your switching frequency, or maybe even 1/20th if you're trying to be conservative. At crossover frequency, then we look at the phase. So if crossover frequency is 28 kilohertz, you look at how much phase is left above minus 180, and that is called the phase margin. So if you draw a line on here and you look at the phase and you look at the minus 180 point, and you see that you've got 63 degrees before you hit minus 180. And again, that is the measure of your relative stability. Any number above 45 degrees, so a phase margin of bigger than 45 degrees is good for most of the applications. And then the gain margin. Now, the gain margin is how much the gain is below 0 dB when the phase hits minus 180. So if you look at when the phase hits minus 180, and then you look at how much your gain is below here, 0 dB, that is your gain margin. Okay, so now we're going to do our next WEBENCH demo, whereby we're going to look at the stability of a power supply. We're going to design a fixed frequency power supply, and we are going to see how WEBENCH helps us with the control loop. The objectives for this one is to design a fixed frequency topology, use WEBENCH Bode plot simulation features to assess the stability, get WEBENCH to redesign a compensator to meet the stability criteria. And here's our specification. Something to note is that you're going from 5 volts to 12 volts. So you're boosting up the voltage. It's an automotive application. The customer is saying that low ripple is very, very important. Therefore, you cannot go for constant on time or decap or any other variable frequency method. You have to go for a fixed frequency. And the customer has specified that the minimum inductance value is 5.6 microhenries. Okay, so we're gonna have to go into WEBENCH and modify the design. A small footprint is not a priority. And low load operation is rare and therefore not a priority. We must have a flexibility to modify the design for future other products, and the BOM cost needs to be less than $5. And you can see immediately now we've got a bunch of filters. To summarize, we are boosting the voltage, we have the space, design must be flexible, we must have low ripple, and low load operation is not a priority. So based on that and what we've talked about so far, a controller IC with current mode control seems to be a very good option, and we're just going to design one in a moment. Okay, so let's go back to WEBENCH again. I'm going to start from the beginning. I'm going to start the design. And this time I know that my input voltage is going to be from 5 volts to 6 volts. I know that the output voltage needs to be 12 volts and 5 amps. So again, I'm going to go for a balanced design. I say view designs. We get this time 27 matches. Okay. Now, again, let us now use some of the filters and narrow this down. So first of all, we know that it's an automotive application. So you can go to IC features and you click on automotive. Have a look at what happens to these 27 matches as I select automotive. There we go. Automotive. It goes down to 13. So from 27, we have gone down to 13. Then control mode. We know that low load operation is not that important. Therefore, we go for peak current mode, and it now goes down to 11. We know that the design has to be flexible. Therefore, we've got a controller, but that's our only choice at the moment anyway. And we know that the BOM has to be less than $5. So if I take that and I reduce it down to $5, we are actually ended up with just one match, which is a TPS 40210 and Q1, which is an automotive part, and all I have to do is customize and design it. So let's click on a customize, because remember the customer said that the inductor has to be 5.6 microhenries. Now, WEBENCH immediately gives you a little alert to say that this is an automotive part, but of course this is exactly what we wanted. Then I close this, and here you can see that WEBENCH has designed everything. These are the compensation components, and this is my output inductor. This is my FET. So I'm going to change this to 5.6 microhenry. So I click on here and I say choose alternative. There we go. You get a whole bunch of alternatives. I can sort them. There we go, 5.6. So I'm going to select this one because the specification says 5.6. Now, when I change that, the entire control loop characteristic changes because I have doubled my inductance. And of course, WEBENCH has designed the control loop based on a 2 microhenry inductor. So suddenly, WEBENCH gives you a warning here. Phase margin is too low. Phase margin is 25 degrees. Remember earlier on when we were talking about the stability, we said phase margin has to be better than 45 degrees. Okay? Now, the good news is that WEBENCH can actually fix this for you. So you open that up and you'll see these are the component values, right? This is the original component values, and WEBENCH is suggesting that you change these or allow it to change it to these values, because with these component values, your phase margin is 25 degrees, but when you adjust it, if you let WEBENCH adjust it, it goes up to almost 60 degrees. So you say apply. When I do apply, have a look at these values. There we go. It has changed them. And now the phase margin has been corrected. So if I go into the values, you see WEBENCH here has fixed everything for me, and now I have got around 60 degrees of phase margin, which makes it absolutely beautiful. Again, I can download the report. Oh, I beg your pardon, this was the bill of materials. I can go to simulate. I can run up the simulation. We're not going to do that because we've already done one and it takes a few minutes. But what I would like to show you is the printout of the report. First of all, again, you can download various CAD packages and you say print report. It's printing the report. And here the PDF is generated. So if I open that, you'll see that you have got the design report. This is the circuit. You've got all the component values. You have got the bill of materials. You've even got the cost of them. And here you get a whole bunch of plots. But in particular, what I'm interested in is a Bode plot, which should be right here. So you can see now that they have plotted the phase and the gain superimposed on top of each other. The red line is the gain, and the gray line is the phase, right? Now, if you take 0 dB and go to this point, you can see that the crossover frequency is around here. And then at that point, you go and see how much phase you've got, and you can see that you've got just above 50. And if I remember correctly, it was 58 degrees. So we have got a very nice and stable design, even though we changed the component values. WEBENCH corrected for us, and our design is pretty much complete. All we have to do is export it. We can order the bits, and our design is done. Fantastic. So let's go back to our presentation, and then we talk about other features of WEBENCH. Okay, so let us now go through some of the more advanced features of WEBENCH. What we do have is some transformer design support now within WEBENCH. So transformer design for power supply is quite challenging. For AC/DC and high voltage DC/DC power supplies, transformer selection and design is actually quite difficult. Often the the available off-the-shelf transformer is not suitable or optimal for the specification, so you have to have a custom transformer. This requires the user to create a transformer using a special cores, core formers, calculate number of turns, the thickness of the wire, winding geometry, and all this sort of thing. And of course, WEBENCH can really help you with this. The Transformer Designer feature of WEBENCH addresses this by making it very easy to design a transformer using a large database of coils and formers. It summarizes the design in a PDF report with all the engineering data available, and then of course you can send that to the transformer manufacturer, or if you're winding your own, you can wind your own sample, but you can certainly speed up the process of designing the magnetics for your power supply. So we're going to demo that now. And also, up until now, we have been allowing WEBENCH to narrow down, using the filters, narrow down and select the actual integrated circuit. This time, what we're going to do is we're going to force it to use a specific chip. So for example, let's say that it's already been decided by management that you need a flyback design with LM5180. And you can actually do that without having to go through all of the filtering processes. You can just tell WEBENCH, okay, design with this chip, it has already been decided. And then we're going to look at the off-the-shelf transformer and versus custom transformer in the tools that is provided, and generate a transformer report. Okay, the specification for what we are going to do is going to be a non-isolated flyback, and then we're going to use LM5180 because the management has already decided that, and input voltage is going to be between 18 to 60 volts, and output voltage is going to be 5 volts and 1 amp, and then we're going to do a little bit of comparison. So to summarize, the choice has already been made. It's an isolated flyback with LM5180, but we need to decide on what type of transformer. Okay, so let us now go back to WEBENCH and see how we can do on this demo. Okay, so here I've got Google. All I'm going to do is type in TILM5180, and here you get the product folder of this particular device. Okay, now with all the devices that are supported by WEBENCH, if you scroll down, you will see that there is a design tool integrated in the product folder. Input voltage minimum is 18, maximum is 60, output voltage 5 volts, 1 amp, and I can just say open design. So the WEBENCH is now forced to use the chip that I have to design with. And immediately it says, click the transformer symbol in the schematic and select explore transformer core bobbin selection to design using a specific transformer core and bobbin. This is the new feature of WEBENCH that we'd like to demo. So the WEBENCH has already designed the power supply for us with all the component values, and it has selected a transformer. So I can click on this and you can see that this is the one that it has selected. I can open up the datasheet for it. Oh, it says file not found. Doesn't matter. Here I have got the coil former from TDK. I have got the footprint. I have got the core type and so on. I can download the report. It's creating a report in PDF form. You can download it, and there we go. Now you can see that all the parts have been specified. Primary, secondary, AWG, the wire thickness, the number of turns on the secondary, the strands, the insulation type, everything is actually being specified. It's a great report that you can, if you're winding your own transformer, you can just use as a specification, or you can send this report to the transformer supplier who will be able to wind it for you based on this specification. Again, you have got the primary inductance, you have got the secondary inductance, you have got pretty much everything that you need in order to design your transformer. So I go back to WEBENCH, and here you can also choose an alternative part, or you can choose an off-the-shelf transformer. And again, if you click on these, you will get the selection that is available for you. It's usually very limited for transformers within a flyback. So whatever is available from a huge database, WEBENCH will have selected for you. Okay, so having done the previous demo, now we're going to show you one of the more advanced features of WEBENCH, and that is the EMI filter design feature. As I'm sure you know, almost everybody needs to pass the EMC test if you want to sell your product, in particular in the European Union. And for power supplies, we typically need to design and add in an EMC filter. Now, in order to sell our product in many parts of the world, we have to pass the EMC standards. There are different standards, CISPA 25, Class 5, Class 4, and these are all defined with big documents and tell you what you need to do. Yeah? The standards specify how much noise a product can emit, emissions, and also how much they have to tolerate before they're passed and before you can sell your product. Power supplies are usually the noisiest bit of the design, in particular around the conducted emissions band, and therefore we almost always have to add an EMI filter. And of course, it's a very difficult thing to do. You must know the standards very well. The addition of the filter can actually make the power supply unstable, and that's the Middlebrook stability criteria and so on. And WEBENCH now designs the EMC filter for us and therefore can save us a lot of time. So what we're going to do is we're going to now use this feature of this WEBENCH. We're going to demonstrate it with a real design example. So the objectives now is use WEBENCH to design a power supply and the EMI filter, learn the EMI filter design capabilities of the WEBENCH, and look at the simulations of the conducted emissions of the power supply with and without the filter. Okay, so the specifications this time is it's an automotive application with high efficiency under high loads. So if I need high efficiency under high loads, from the previous discussions, we're looking at synchronous rectification. Then you must pass CISPA 25 Class 5, which is an automotive standard. And then the customer has specified the line impedance as 50 ohms and with a series inductance of 5 microhenries. Okay, then the input voltage is going to be between 4.2 volts and 12 volts, and output voltage is going to be 3.3 volts, 600 milliamps, with an efficiency of better than 90% and a total BOM cost of less than $3. So you see, that can immediately narrow down our design as to what we can and cannot select. So to summarize, it's automotive, needs to have synchronous rectification, high efficiency, specified BOM cost this time, and now we must add the EMI filter in order to pass CISPA 25 Class 5. Let's see how we can use WEBENCH in order to design the power supply and the filter. Okay, so looking at WEBENCH again, I start a new design. I know that my input voltage is going to be 4.2 volts to 12 volts. I know that the output voltage is going to be 3.3 volts and 600 milliamps. I go balanced and view designs. You can see that we have got 223 matching designs. Okay, we need to narrow these down, but now we should be really familiar with how to use the filters. So if we go down the filters, on the last one there's features, and you can see that some of these are WEBENCH is enabled to design the EMC filter for, right? So I'm going to click on that, and that goes to 95. So it drops down from 223 to 95. That is good. These 95 designs are the ones that WEBENCH can design the EMI filter for me. So then we know that it's going to be automotive. So I can go to features. I can select automotive. It goes to 47, and synchronous rectification. Oh, it seems like they're all synchronously rectified anyway, but we also know that the efficiency has to be better than 90%. So if you have a look at these 47 design matches, I now increase my filter for the efficiency. You can see the number of designs dropping. And I'll pull it up so that it is more than 90. Okay, suddenly 47 drops down to 20. And I know that the BOM cost has to be less than $3. So again, I go to BOM cost and I make sure that all the designs, again, you can see from the gray bars, right, the number of designs that are disappearing is less than $3, okay? $3. there we go. We end up with 5 designs. All of these are suitable for our application. We can compare them if you wish. Let us just select the first one, which is this one. And soon WEBENCH will open up the design. I beg your pardon, this was the data sheet. So let us customize. That's it. It gives me an alert to say that it's an automotive part, but that is exactly what I want. It has designed everything for me, but at the moment you can see there is no input filter. However, I've got here an option to add an input filter. So I say input filter. Now, I can select which standard I want it to comply with, but we know that it's CISPA 25 class 5. And these spikes show that the power supply is failing at the moment. The gray line is the pass line, and any spike that is above the pass line means that the power supply is failing this standard. So I press next. Here, WEBENCH asks me a couple of questions. In particular, I need to input the line impedance, which is specified by the customer as 50 milliohms and half a microhenry. I press next. And based on that, WEBENCH has now designed my differential mode filter here. I have got my inductor, I have got my capacitor and its damping. It's got the values for these. And have a look at this. Noise before filter was 96 dB microvolts, and now noise after the filter is 59 dB microvolts. Now, this is the circuit diagram of the filter with the component values. This is the input current. You can see the classical shape of the input current before filtering or with no filtering. Then this was the harmonics before filtering, and you can see that many of them are above the gray line, which means that the power supply is failing. The standard filter components that we have to solder on is given here. And this one is the spectrum after filtering. And you can see now that all the noise has been attenuated down to below the gray line, which means that now, at least under simulation conditions, we are going to pass. And these plots are showing you the input impedance, output impedance of the power supply and the filter, and this is the Middlebrook stability criteria. This is just showing you that the filter that WEBENCH has designed is not going to mess up with the stability of the control loop. That's fantastic. So I can now just say add to design. Now we go to design, and you can see that this filter has been added to my design. So in addition to the power supply, I now have an input filter. I can simulate it if I wish, but we have done simulations before, so I won't bother doing that. However, what I can do is I can export. Again, here I see the PCB layout, I see the circuit, including the EMI filter. I can download various CAD files for it, and I can print the report. So I print the report, creates a PDF file for me, and then I can open this, and you will see now I have the design, I have the bill of materials, then I have got a whole bunch of graphs which gives me the data that I need, but what I'm interested in for this example is the input current and the filtering. So there we go. This is the control loop like we discussed before. You can see the gain plot and the phase plot. So you can look at the phase margin and the gain margin and the crossover frequency like we discussed. This is the input current before filtering. And here are the plots that I'm interested in. There we go. This is the current harmonics online before filtering. And you can see that many of them are above the gray line and therefore be failing. And of course, now that we have added the filter, it is now under the gray line, which means that we are passing. Fantastic. Now let's go back to the presentation. So finally, what are we going to do next? Well, you can launch the application from this link over here. Also, very easy way of getting to it is just type into Google TI and WEBENCH, and that will be your first hit. If you've got any questions, you can go to E2E, whereby you can get some help and support. And perhaps after you become a little bit more confident in using WEBENCH, you can use some of the more sophisticated chips, such as this one. There are some very nice advanced configurations options within WEBENCH, so that you can perhaps change the load transient specifications and things like that. Hope you enjoyed the webinar, and hope to see you at one of our future workshops. Thank you very much for listening.